Okay, so I have opened this example building. It is a 10-story building, very regular building with moment resisting frame and shear wall, concrete moment resisting frame and concrete shear walls. It has both a core wall and few planar walls also. So the loading actually automated lateral loading or any loading actually is defined like this in ETABS, that you first make a load pattern in define menu, and that pattern is called in the load case, and analysis is run for load case, and then those results of those load cases, they are combined using different load combinations which you can define. So first is load pattern, then is load case, and then is load combination. The analysis is run for load cases, but the design is performed for load combinations. And in order to make a load case first we have to define a load pattern. So pattern includes the automated seismic loading, automated wind loading, or any other type of loading. So even if you want to manually apply some point load or a uniformly distributed load or area load, you have to include it in some pattern. So definition of load pattern is the first step for the application of loading in ETABS. So once we complete the structural model and we want to apply the wind loading to this model for the purpose of design against wind loading, so we will start our process with define and load patterns. So I go in load patterns and then I can give a name of some load pattern, for example wind load, and then its type should be wind loading, this one. So there are some predefined types for each load you can select. So wind is there already, so I selected the type wind. Self weight multiplier obviously will be 0 because it should only be included in the self weight load pattern or dead load pattern only. And then here there is a list of all the available building codes using which the program can automatically calculate the wind pressure and then convert it into wind force and then apply and perform the analysis. So the very first one is exactly ASCE 7-16, but there are some other codes also. UBC 97 in this version is still there, Indian code, Canadian codes, other versions of ASCE 7, older versions like ASCE 788, 95, 702, 05, and then 710 also. User loads also, where you can manually define your own loading values manually after manual calculation. So you can go for that option if you want to go. Italian code, then Korean, and some other code, Chinese code, Euro code, it is all available. Similarly, Australian and New Zealand codes also. So let's select ASCE 7-16 and add new load. So you can see here that one row is added here. There was a previous one also which I just defined earlier. So this one is the new one, the last one. So once it is added, I can modify, click on modify lateral load to open the same form which I showed in the slides. This is that form. So here all the inputs which are required by the program to determine the design wind pressure according to ASCE 7-16, you have to provide that all those inputs. So all those coefficients and exposure category and everything, you have to provide it here, right? So let me skip this first part and I'll come back to it after. First thing is the wind pressure coefficients here. So either you can ask the program to determine it for you based on ASCE 7-16 tables and figures and everything, or you can determine them yourself and provide your own values. You can directly pick from the table itself and can give your values, or you can also define your own values depending upon what input data you have. So the value of wind pressure coefficient Cp for windward side and for leeward side should be provided here. So if I go back in the slides and directly show you that CP table. I think it was, yeah, this one. So you can see here that for windward side, depending upon L over B, you will select your CP number. And similarly for leeward side also, you can pick a CP value. So those values you can also directly give as a user defined number, or you can ask the program to determine it for you itself. It will follow ASCE 716 to pick that number for you. Second thing is the wind exposure parameters. So here you have to define wind direction and exposure width. If I click on modify show, it will give me all the diaphragm list and its width and depth and ordinates and the direction angle. So wind direction angle is currently by default equal to 0. You can also convert it, you can also have a 90-degree angle, and then you can make a separate case if you want for 90-degree. So actually what program is doing is that it will calculate the exposure area based on the diaphragm dimensions. So the definition of diaphragm is actually the first step I should have told you before actually start making the wind load this pattern. So actually if I go back and if I just click OK, so here you can find an option to define a diaphragm, define and diaphragms. So there are two types of diaphragm which you can have. One is rigid diaphragm, which is a rigid constraint, and then you have a flexible or semi-rigid diaphragm. So if I modify this one, currently only one diaphragm is defined, which is defined as, it is given a name D1, and it is rigid, right? I can make it semi-rigid also or rigid also. So currently D1 is rigid, and after we define that diaphragm, we have to assign to each floor also this particular diaphragm in order for the program to determine the exposure area based on diaphragms. So actually I have done that already, but if I just tell you one particular example, so let me open the plan view and go to maybe the story 1. So the procedure to apply that rigid diaphragm or any semi-rigid diaphragm also to this particular floor is that I select that floor and then go to assign and then shell, and then this is the option for diaphragms here. So I can click on diaphragms and then select from that list whatever diaphragm I have defined earlier. It is D1 already, so I can click on D1 and then just apply. So this symbol which you have seen here, these dotted lines converging to the center, is a symbol for the rigid constraint. So what program actually does is that it joins all the nodes on that floor level with a master node created at the center of mass using rigid links. So all the slave nodes, they have the same deformation or same lateral sway as the master node. So this is the concept of rigid constraint at the floor level. So you can do that for each level. Currently if I go up, you can see that still the same diaphragm level is, that diaphragm symbol is being shown, because I have already assigned to story 2 also, and then story 3 also, story 4 also. I can keep on going up till the last level. So I have defined for each story this rigid diaphragm option already. So the program knows already, it is able to calculate the exposure area based on the elevation difference between two diaphragms. So program already is able to calculate the exposure area based on my diaphragm definition. So this is something which you have to first do even before started making the wind load pattern. Define diaphragm and then assign it to your floors. It can be rigid or it can be semi-rigid also. And the program will actually apply one force value at each floor if you go for rigid option, and it will distribute that force into different elements in horizontal direction for each floor if you go for semi-rigid option. So this is the point I wanted to make here in, I think, the last slide, that here that if you go for the rigid diaphragm option, here for rigid diaphragm option, the program will only calculate one auto-lateral load at each story, which is applied at the center of mass, right? So for rigid diaphragm option, only one auto-lateral load at each story and applied at the center of mass. For semi-rigid option or flexible diaphragm option, the program will not apply just one load at each story. It will distribute the auto-lateral load along the perimeter of the building. So if I just make one particular floor level, like let's say this is the plan view of one floor level and this is the center of mass. If I apply the rigid diaphragm option, the program, and let's say it is applying force in X direction, the program will just apply one total force for that whole floor. It will simply apply it at the center of mass. But if I go for the semi-rigid option or flexible option, then program will divide that force along the perimeter. Let's say that there is a column here, there is a column here and here. The program will divide this force into three forces and apply and distribute it along the perimeter in that particular direction. So you can even see that in ETABS, once you make the wind load case, then you can have an option to view the applied wind loading also. And for rigid case, you will see only one loading per floor. But for semi-rigid case, you will see several loadings per floor, which are distributed along among different lateral load resisting elements, for example, columns and shear walls. So this definition of diaphragm should be actually your first step, and then you can go to define and this load patterns, and then you can make a ASCE 7-16 auto lateral load pattern. We can modify this one to see that form again. So here this was the thing which I was actually skipping first, that exposure and wind coefficient. The program now need to know that what is the exposure area to convert the calculated wind pressure into the wind forces. So one option is that we just directly define the diaphragms and ask the program to take the exposure area from the extents of diaphragms. So this is the default option here in ETABS. If we go for this option and then click on wind exposure direction and exposure width and click on modify here, we will see that program will list all the stories and the diaphragms, and the widths and depths are already automatically calculated by the program. So it already knows the exposure area, how much area is required to convert pressure into force. We can also convert it into user defined. The exposure set width is user defined if we click on this option. In that case, we will be able to modify any row or add a new row or delete a particular row. So these options are available to you if you go for user defined option. Otherwise, the program can auto calculate the diaphragm extents, and in that case it will directly use these values to calculate the exposure area. So let me click on OK. Let's keep it as program calculated. Now this one is case option, which is figure 27.3-8. This is the one which I was talking about, that by default is create all sets, and 1, 2, 3, 4 is actually the load case which is defined by that particular figure in ASCE 7-16. So if I go only for case 1, I know that it is applying only forces in X direction and Y direction separately and no other case. Case 2 I know already, but if I click on create all sets, it will create all 12 sets within one load pattern. So no need to create separate load patterns for X direction, Y direction, X direction plus eccentricity, Y direction plus eccentricity, etc., etc. So all 12 sets can be created within this load pattern. So if I click on this I symbol, the same table is shown here, which is telling us the detail of how the program has calculated the 12 sets of loading. So when I make this load pattern and click on create all sets, actually I am applying 12 loadings separately. Each one of the set is being applied separately and the response is being calculated separately and it will be reported separately also, right? So all 12 load cases, which are basically 4 cases and converted into 12 due to different directions and signs of eccentricities. So all will be applied if I click on create all sets. Then eccentricity in one direction, eccentricity in the other direction. By default it is 0.15. If we want to change is this number we can change, but ASCE 7-16 prescribe that it should be 15% of the dimension of diaphragm in the perpendicular direction. Then wind coefficients, it is design wind speed in mile per hour. We have to provide that one from the wind hazard map, which we discussed already. And that map is again dependent on the risk category of your building. So different risk category buildings have the hazard, which is for having a different probability of exceedance in 50 years. Exposure type you have to select from B, C, D. So this is also manual calculation. You have to first categorize your surface roughness and then based on that height of the building, how much distance that roughness is, you have to decide about the exposure type. So you have to select it yourself, B, C, D. Ground elevation factor, topographical factor, gust factor and directionality factor. All those factors should be, 4 of them should be given manually. You have to calculate or take it from the tables manually and put it here. Exposure height, what is the top story at which the loading should be applied, what should be the bottom story. So you should select the full, here I select the full extent of building to apply the wind load. Include parapet, if we want to include a parapet then we have to give a height of that parapet wall also. Let's just not include it. So this is all what is required by the program to determine P, which is the design wind pressure. And then using this exposure thing, it will convert it into force, and depending upon whether you give a rigid diaphragm or semi-rigid diaphragm, it will apply the loading one at each level if we go for rigid, and several loadings at each level, distributed loading if we go for semi-rigid. If I go for the exposure from frame and shell objects, then I can click on include shell objects and then I can manually apply the pressure coefficient in different shell objects. If I go for frame objects, that option should be for open structure, right? So then we have to also give solid over gross area ratio. This is an additional input which is required only for open structure. So you can see that if I click on this option, this is alive and also the wind direction is also alive. If I don't click on this, the option is not available. So if I click on exposure from frame and shell objects and click on include shell objects, you can see here that no wind pressure coefficient is required here, because in this particular case you are required to manually give the pressure coefficient to your shell objects, which means you have to manually apply the cladding to your structure. You have to model that cladding. There is an option for auto cladding also, I'll show you in a minute. But to those cladding elements you have to give your own pressure coefficient, and that will be converted into pressure and force to be applied to your structure. So all of the inputs required here about the wind direction and the pressure coefficients, they are not required if you go for the second option, because in that case you will be giving your own values to specific shell objects, which can be the cladding objects, right? So if I go for the first option, then all of the options are then available, right? So if I click on OK and go for the first option and click on OK again, I have already defined a wind load pattern, and if I go for define and load cases now, I will see that one load case for this particular pattern is already defined by the program. So when I define a pattern, the load case for that pattern is already defined. So wind load case is already defined. I can modify that to review that case, and I will see that what analysis type is being assigned. So you can see that this is a linear static analysis, and it is simply applying the wind load pattern with a scale factor of 1 to my building, right? So this is automatically defined when I define a load pattern. So I can click on OK, and now this is defined. So when I run the analysis, this load will automatically be applied, and the results will be available for all of the cases which I select in that pattern. So since I selected all 12 cases, or all actually 12 sets of loadings, so the results for all 12 will be available. So I click on OK, and I think even before running, let me check whether we can see the auto lateral wind loading or not. So I can click on display load assigns and then joint loading, and let me select the wind load which I just defined, this pattern. So I click on forces and then apply. So let me see if I can see. Let me open a 3D view. So maybe I think this option is available once the analysis is run already. Otherwise, I should have seen the one loading at each floor applied as the wind loading. Program should have already calculated and then shown here as point loads, one at each floor, because I used rigid diaphragm. But I think I should first run the analysis to view those loadings. So one thing is about the second option in exposure. So let me cover that one also before I run the analysis. So in the same load patterns, if I go for the second option, let me modify that load also, modify lateral load, and let's select the exposure from frame and shell objects and include shell objects. So now all the information here is gone. I have to manually include cladding and apply the pressure coefficient to those cladding. So I can click on OK and again OK. Now I can go for one option which is here define, actually here draw, and here is auto draw cladding. So if I go for this option, the program will automatically cover my building's exterior with null shell elements which are representing the cladding. So let me click on this option, draw auto draw cladding, and it is saying that should I use floors or beams or columns. If I want to draw cladding using beams, I should first select those beams so that program can draw the cladding there. But let's select use floors here and click on OK. So you can see here that program has covered all my building with exterior of my building with null shell elements. So I can also modify it. I can delete some cladding elements which are not appropriate or which are not there in actual building. So if I click on any of these auto cladding elements, let me click on any element, shell element. Maybe let me zoom in a bit to click on some cladding element. Let me unselect that one. So okay, I right click this auto cladding element, and you can see here that it is having a section property which is none, which means no section is assigned to this cladding element. Similarly, no property modifiers, no loading. If I click on loading or any other thing, all the parameters are none. No mass. So here you can see no mass and no weight, obviously. So this is a null element, and the purpose of this element is only to tell the program that this is an exposure area which should be used to convert the pressure into forces. And then we can also select all of those cladding elements and assign our own you can say pressure coefficients. So for example, let me select this particular cladding element which is selected now, this particular one, and after selecting this I will go to assign shell, and then you will have actually I should go to shell loads, and shell in shell loads we should have a wind pressure coefficient option. So here I should apply the wind pressure coefficient for windward and leeward side. The same CP value which we can take from ASCE 7-16, we have to apply that in the wind load pattern. So this wind load was our pattern name, and I can give, let's say, 0.5 or any other number in windward as well as in the leeward side. So when I apply that, you can see here that the symbol on that particular shell element is visible, showing the windward direction and the value of that particular coefficient 0.5. Similarly, in the leeward side, I can give the number and apply, and that will be given to the leeward side. So let me click on this option. So we have to select all the shell elements which are representing our cladding and perform this assignment, assign to shell loads here and then wind pressure coefficient. For all the leeward side we have to select and then apply that. Similarly, for all the windward side we have to select and apply that. So you can use the selection tools available here by the property type or by the object type. You can select all of them in just one go and apply in the windward and leeward side these coefficients. So in this way you can directly tell the program that this is the coefficient and this is the area on which this coefficient should be applied. So it will be calculating your wind pressure or wind loading. So if I convert the diaphragm into semi-rigid diaphragm, again we will see that if we go for the extent from diaphragms option, we will see that several of the loadings will be distributed at the periphery of the building in one particular direction. So now let me open the same model, but it is run already for this wind loading. So let me quickly go through some of the example results once we run this analysis. So this is the same building, but now the model is locked. It is already run. So let me directly go to analyze and then set load cases to run. I can see here that the wind load case is run already, it is finished already, so the analysis results are available now. So all the results, as you know already, that they are available in this display tab after running the analysis. So let me start with the story level responses, story response plots. And so you can see here that in this table we have to first select the what things to see. Let me first go for the maximum story displacement, and then the load case is wind, and within that load case there is a step number. Now step number is actually that load set number. So you will see that you can go from 1 to 12 and each step is representing the results of a particular load set, right? So all the 4 cases prescribed in ASCE 7-16 are covered in these 12 loading sets. So step 1 means the set 1, and if you remember, set 1 was then when the loading is applied only in the x direction separately. So you can see here that the y direction displacement, which is shown here by red color, is all 0, and the building is only showing the displacement in x direction. It means that the loading was applied in x direction only, and since the building is regular, x direction loading is only producing the deflection in x direction. There is no rotation of the building or no inherent, you can say, torsion in that. So if I change this to step number 2, which means the load case set 2, if I click enter, I can see that now the x direction deflection is all 0, and only there is a y direction deflection. And similarly, if I go for step number 3, now it is Step 3 was that x direction loading is applied, but at the same time some torsional moment is also applied. So you can see here that now the deflection is mainly in the x direction, but also there is some deflection in y also, which is because of the application of torsional moment. Let me go for any other step, let's say step number 8. So you can see here step 8 I think corresponds to the load case 3 maybe. Yes, load case 3, in which the loading is applied on all four sides and there was no torsional moment. So you can see that the deflection is comparable in both x and y directions for this particular step number 8. We can also directly go to step number 12, which is the most comprehensive. And if I just select any other number, let's say 15, it will automatically revert to 12. So maximum we can go to 12. So all 1 to 12 is actually the load sets which were applied by the program. Similarly, we can also see the story shears, for example, for all four sets. So story shear will be plotted in that step manner. Similarly, for any other step set of loading, let's say 6th, I can plot the story shear, or I can also go for overturning moment or any other loading. So there is a list of all the story level responses: diaphragm drifts, diaphragm center of mass displacement, and more importantly we can also see the autolateral loads to diaphragms. So if I click on this option, it will directly show me what loading was applied actually what loading was calculated and applied to each of the diaphragm. So you can see here that the exposure area for story 10 was very small, so it is a very small force. Similarly, you can see other numbers also. For different load sets from 1 to 12, you can see, for let's say I click on 9, you can see x direction in blue color, y direction in red color. For step number 12, I can see, right, so all the forces are visible here, x direction in blue color, y direction in red color. So one thing is that maybe in the three-dimensional view also I can see the forces, applied forces now. Let me go to display, load assigns, joints, and let's select that. See here you have now all the 12 cases of wind. So let me select first one of 12 and click on apply. So you can see here, although it is not very clearly visible, but you can see the point loading applied at the center of mass for each floor. If I click on the plan view, so at each plan level I can see one force applied at the center of mass. So you can see this 53.98 is the floor loading which is calculated for this particular load set 1. For load set 2, this should be actually in y direction. So see, you can see this number is now in y direction. Similarly, for load set 3, it should be loading in x direction and a torsional moment. So you can see here it is actually loading in x direction, and torsional moment I think is not clearly visible. Maybe let me go for any other step. You can see here this was a case where both of the loadings were applied simultaneously in both sides, so it is shown here. So you can also graphically see those loadings and their values can be seen in the story response plots here. Similarly, you can see the deflected shapes. Go to display, deformed shape, and in that also you can easily visualize that in those steps or those load cases where the loading is applied in both direction, you will see that building will be swaying in a diagonal direction, and in those cases where the building is applied with one direction at a time, building will be primarily swaying in that principal direction. So let's say I apply for step number 1, it should be x direction loading only without any y direction loading. So I can click on OK and go to the display model. It will be showing that building is primarily swaying in the x direction. So we can animate that one also to visualize how the building will deform or sway under a particular load set within the wind load cases. So in the torsional cases, you will be seeing the effect of that torsion also in the deflected shape. So again, I will go to display and maybe directly go to show tables, or maybe here one feature I want to highlight here is the in the story response plots. Here in this tab, there is an option to show the tabular values of these graph, whatever is being shown. So it is, if you click on formatted, you will see all the data which is shown graphically. You can simply see it in the form of table, and by clicking on this button you can directly take it to Excel and plot it yourself also. And also there is an option for report, and in that you can generate a summary report and a detailed report. If I click on detailed report, you will see that the view which is being shown here, all the information about that view and its tabular data is generated in the form of a report, which can be saved or which can even be exported to a Word document. If I go for a summary report, then maybe just one page of that view only. This is a very handy tool which can be directly used, and this can be generated for any type of any type of the result which you can plot, for example story moment or drift or any other response. So let me see if there is anything else left. Although you obviously you can see the forces also, just like any other loading. You can plot the shear force diaphragm, you can diagram. You can plot the bending moment diagram. You can see the shell stresses, and also you can see the reaction support reactions at different support, you can say, restraints. So all the results which you can see for any other loading, static loading, you can see here also. So I think that's all about this demonstration. The detailed results are available in show tables. In that you, I think, are familiar already that all the analysis results are available in this particular area. You can check or uncheck a particular type of result, and this will generate a detailed table which can be sorted out to finally extract any result which you want, any component level response, or for example shear force in a particular column or bending moment in a particular beam or any other response. So all those detailed tables are already available. One last thing is this option. In the Model Explorer option, there is a Reports tab also, and you can develop a project report here. You can click on this option, actually double click on this option, and this will generate a project report for this particular analysis which you have just performed. So now it is saying generating report, so it is actually sorting out things to include in that report. So now we have this report generated already, and it contains all the information starting from inputs up to the analysis procedure and finally the results. All those detailed tables are listed. So it is a very detailed report, and uh, you can save that for reference, and maybe later if you want to find any data without even opening the model, you can check that particular number from this report. So this is also sometimes very handy to generate a complete report and keep it for your future reference of any output which you want to see at some later time. So I think that's all about this demonstration.